Welcome to Network Theory. Today's video is on mesh and supermesh analysis. The references which have been used are Ravi Singh Circuit Theory and Networks, William Haight Electrical Circuit Analysis, Charles Alexander and Sediku Fundamentals of Electric Circuits. Okay, so we'll be discussing about mesh analysis and supermesh analysis techniques here. Okay. Now, what do you mean by mesh analysis, or what is a mesh? A mesh is a loop which does not contain any other loops within it. So, when we are discussing about electrical circuits, this is the most common. We have a circuit, and for a circuit, we need to have a closed loop. So, all circuits, most of the circuits which we have, we can see a loop. Now, what is a mesh? It is the smallest loop, which means there are no other loops within that, right? So it is useful if the network has a large number of voltage sources. So normally in mesh analysis, we write KVL. So KVL is what is used for mesh analysis. The Kirchhoff's voltage law in terms of unknown mesh current. So normally in mesh analysis, we write the voltage, the expressions in terms of unknown mesh currents which are decided. Okay. So what are the steps for mesh analysis? So first, let's see a mesh, a typical example of a mesh analysis. Here we can see there are three loops or three meshes here. So this is the first mesh, the second mesh, and the third mesh, right? So when we are starting with the steps for mesh analysis, first what is done is identify the mesh and assign unknown currents in the mesh, or you assign currents to the mesh, which are called as mesh currents. Now assign directions to the currents. So these are directions. You are going to be randomly assigning the directions. So in the mesh, these I1, I2 and I3. So here we have just randomly assigned clockwise directions. So it could be any direction, but we are just randomly assuming three directions for the three meshes. So three mesh currents which are unknown. So mesh, remember that mesh currents are supposed to flow in the whole loop. So this is the first mesh. So I1 current is going to be flowing in this mesh. I2 current is flowing in the whole mesh. So mesh current is different from branch currents. Please note this. So assign the polarities for voltage across the branches. Now the polarities are depending upon how it is when we go around the mesh in the direction of the current. The polarities are assigned in such a way that you have if the current direction is something like this, then it means that current always flows from higher polarity to lower polarity. So which means that, so if the current is flowing through an element resistance in this direction, the resistance polarity, the voltage across the resistor will have the polarity like this, because current always flows from higher to lower polarity. So this will be plus and minus. So this is what you mean by assigning the polarities. Then you apply KVL around the mesh and write the KVL equations and solve the equations for the unknown mesh currents. So this is basically the step for mesh. And okay, so this is a problem. We have to find the current through the 5 ohm resistor, which is this one, the 5 ohm resistor. You're supposed to be finding the current through the 5 ohm resistor. So when so you can identify that there are three meshes. So once 1, 2, and 3. So first, once we have identified, we will assign currents for this. It is assigned in the clockwise direction. It could be anti-clockwise also. It is purely random. So once we assign the direction, so it looks like this. So we have given an I1, I2 and I3, and it has been assigned clockwise directions. Again, I'm saying it is just random assumption. If the assumption is wrong, the currents which we find out after solving will be negative. That is the only difference, but it is fine. So you assign the directions. Always better to keep all the three in the same direction. Now, once we do this, we are going to be, the next step is you assign polarities for all the voltages across the different elements. So how do you do that? As you follow I1 in the first loop, I1 is flowing like this through the 1 ohm. So this would be a plus minus, because the current I1 is flowing like this. The current I1 is flowing like this. Again, I1 is flowing like this. So this is the flowing in the downward direction through 3 ohms. So this will also be plus minus, right? Now, plus minus for I1. But at the same time, you can see, so here I'm not this is for I1. Now, as I2 flows, so according to the direction of I2, this is going to be plus and minus here. So you can see that the 3 ohm is common to the meshes 1 and 2. So 3 ohm is common, this 3 ohm is common to the 3 ohm is common to the meshes I1 and I2. So it will have, so according to the direction of I1, the polarity is like this. According to the direction of I2, the polarity is like this. So which means that, now this is one thing which we write. When I'm writing the equation for mesh 1, the current I1, because we are concerning I1, so I1 is considered to be higher, or it is predominant here, right? Because 3 ohm is common to both the meshes. Similarly, we have got a 6 ohm, which is common to both meshes I1 and I3. So according to the direction of I1, the 6 ohm will have a plus minus like this, as shown. So this would be plus here and minus here according to the direction of I1. But according to the direction of I3, it would be like this, plus and minus, right? So when I'm writing KVL, how do I write KVL here? So going around the mesh 1 in this direction, clockwise direction, like this. So let me write KVL in the direction. So minus 2 plus 10, minus to plus is a as we go around this. So I'm starting from the voltage source, right? So when we are going in this direction, from minus to plus is a plus 10 volt. Then we are going through the 1 ohm resistance, right? So again, plus to minus is a drop in polarity. So you're going to be writing it as minus 1. This one, 3 ohm, across 3 ohm. So first let me write for the 1 ohm, so minus 1, and the current is I1. Now the 3 ohm is common to both the meshes 1 and 2. So which means there is a current I1 and there is a current I2, which are both in opposite directions. I1 is flowing down, I2 is flowing up. So effective current is I1 minus I2. And we write it as minus 3 into I1 minus of I2, because we are following the direction of I1. We are assuming that I1 is predominant because we are following the mesh 1. And last one, minus. So we have reached the last element, which is of the mesh 1, which is the 6 ohm. 6 ohm resistance. It has got currents of I1 and I3 flowing in it. Again, I1 is flowing down, I3 is flowing up. So effective current is I1 minus I3. So in the same way, I write minus 6 into I1 minus I3 is equal to 0. Again, see that this is a plus to minus. So plus to minus is a drop in polarity. It's a drop in polarity across the 6 ohm. So minus and following I1. So the resultant current, I'm writing it as I1 minus I3. Similarly, write the KVL for mesh 2, again going in the clockwise direction, because the direction of I2 is like this, going in the clockwise direction, right? So maybe I'll start from 2 ohm, then go to 5, then here follow this and reach 3 ohm. So that is how I'm going to be writing the equation. So minus 2, minus of 2 into I2. Okay, again 5 also has got I2 only, this one, this one. So this is plus minus, this is plus minus, and this is 5 volt has a positive and negative. So when I'm going from positive to negative, it is minus 5, and then again minus of 3 into I2 minus I1 is equal to 0. See, when we were speaking about of mesh 1, the 3 ohm was common to 3 ohm was common to mesh 1 and mesh 2. So I wrote it as I1 minus I2. Here I am writing it as I2 minus I1 because I am writing the equation for mesh 2 now. Now the last one is mesh 3. So mesh 3, again following the clockwise direction for I3. For 4 ohm, I3, the 4 ohm has only I3. Then there is 20 volt, and then the 6 ohm is common to I1 and I3, common to the meshes 1 and 3. But since we are writing the equation for mesh 3, I'll write it as I3 minus I1. So the equation is going to be starting from the 5 volt source. Minus to plus is a 5 volt minus 4 I3 plus 20, because we are having a minus 2. So I'm going in this direction. When I'm starting from this direction, minus to plus is plus. Then again in this direction, 4 ohm has the current is flowing like this. So 4 ohm, the polarity is going to be plus and minus. So it is a drop in polarity, which is minus 4 I3. And then the last minus 2 plus 20 volts. So plus 20. And the last one is 6 ohm. So which is minus 6 into I3 minus I1 is equal to 0. And see that the 6 ohm resistance. So when we are going like this is a positive to negative. So minus 6 into what is the current? I3 minus I1. So what we keep in mind is that when we are writing the equations of particular meshes, for this is for the first equation was for mesh 1. This is for mesh 2 and this is for mesh 3, right? So these are the corresponding equations for each mesh. So, or maybe I'll not write it like this so that it'll get confusing. So here this is for mesh this is for mesh 1, this equation. So when I'm writing for mesh 1, mesh 1 current is considered to be higher or predominant. When writing for mesh 2 current is considered to be higher, and when writing for mesh 3 current is considered to be higher. So this is how we write particular equations. Now when we solve this, once we solve we can get the answer. You have asked the current through the 5 ohm resistor. Now the 5 ohm resistor, the current is equal to I2. So once you solve it, so solve and find. So once we solve, we get the equations as I1, I2 and I3. And since your 5 ohm resistor current was equal to I2, I2 is the same as I4, I5. That is the current through the 5 ohm resistor is found out to be equal to 0.78 ampere. Right? So this is how we have done the problem. Okay. The next case. So we discussed mesh analysis. Now the next case is mesh analysis with current sources. So when we are speaking about this case, what we have is, what is a super mesh? Meshes that share a current source with other meshes, none of which contains a current source in the outer loop. This is a super mesh, which means that when we are having a current source in between two meshes, we call it as a super mesh, right? So when we are solving supermesh equations, how do you do it? Total number of equations required for the supermesh is equal to the number of meshes contained in the supermesh, which means that suppose there are two meshes and you have a current source in between them, then it is called as a supermesh. So suppose you have a current source in between. So you have something like this. You have elements here and you have elements here, right? So here this is one mesh and this is the second mesh. So this, since there is a current source here, we call it as a super mesh. Now how many equations? So for the super mesh, how do you solve it? You have got two equations. There are two meshes involved. So mesh 1 and mesh 2 are involved in the super mesh. So these two are called to combine together is called as a super mesh. Now suppose you call this current as I, right? Now the currents through the mesh I1, I call it as I1. Through the mesh I2, I call it as I2. So first thing, how do you write the super mesh equation is that you first write a KCL for the current source, right? A KCL equation is written for the current source, and how do you write it? KCL can be written as I is equal to, this is the equation this is the current source is I, and how do I write the current? This current source is common to mesh 1 and 2. So in terms of I1 and I2, I can write I is equal to I1. I1 is flowing down, right? I1 is the current which is flowing down, I2 is flowing up. and current I, this current source I is also flowing down. So it's basically following the direction of I1. So we can write that I is equal to I1 minus I2. It's a resultant current, right? So now the first step is done, that you write this is the KCL equation. Now you write a KVL. So the second step is that the remaining equations are KVL equations. So the KVL equation, how are you going to write the KVL equation is by first ignoring the current source. So you have written the current source equation already, right? Now remove this current source, remove the current source and go through mesh 1 and mesh 2 as if there was no current source. So this is mesh 1 with the current source. I remove the current source and this is mesh 2. So I go around mesh 1 and mesh 2 without the current source and then write KVL for this. So if I write KVL, so all these elements, so if I designate this as R1, R2, R3, so I'll go around the loop like this without the current source. So write the equations. So basically these again when we are writing for super mesh, what do we write is we first identify what is a super mesh, how many meshes are involved in the super mesh. So here two meshes are there and they have a common current source. Write the equation of this common current source in terms of the mesh currents. Then write KVL by ignoring this current source has already been considered. Now remove this, then write KVL for the remaining mesh 1 and mesh 2 without the current source. So these are the steps which we follow. Okay, so here we have a problem with the super mesh. So you can see that there are two meshes here. There is a current source which is common to these two meshes. So which means that the current source is common to these two meshes, and so this is a super mesh problem. So whenever there is a current source, normally we have voltage sources when we write mesh analysis, but here we have a current source. So that is the difference. So whenever we have a current source, we are not able to write the voltage of across the current source. For every element, you need to write KVL when we are writing mesh analysis. But that is not possible here. So we write KCL, not KVL for the super mesh. So let us write KCL for this particular super mesh. What is the KCL? You consider the current 6 ampere, which is flowing through this particular branch. In terms of the mesh currents I1 and I2, it is nothing but I2 is flowing upwards, I1 is flowing downwards. 6 ampere is also flowing upwards. So I can write 6 is equal to, the current is equal to I2 minus I1. 6 ampere is flowing upward, I2 is also flowing upwards. So effectively I am writing it as I2 minus I1. So this is one equation we have. Now the second equation we write is KVL. KVL for the super mesh. How do you write KVL? You exclude or you remove the current source, and if there is a resistance in series with it and the 2 ohm resistor, because basically it is like you are removing this current source, this branch from here, right? So once we remove this, then we are able to write KVL for the remaining part for mesh 1 and mesh 2. So mesh 1 and mesh 2 or super mesh, which means so mesh 1 and mesh 2 are considered together, right? So instead of writing a separate equation for mesh 1 and another separate equation for mesh 2, we are going to be writing mesh 1 and mesh 2. So by excluding this element, so which means what, we go along this loop like this. So this is mesh 1, this is mesh 2, and we come back here. Now while writing this equation, see that you have just eliminated here the current through 6 ohm is I1, current through 10 ohm and 4 ohm is I2 only, right? So we are going along the loop writing the currents in terms of the mesh currents. So KVL for the super mesh is going to be like this: 20 volt minus 6 I1 minus you have 10 ohm and 4 ohm, and the same current flows through both. So I write it as minus 14 I1 sorry, minus 14 I2, right? So I've gone along the loop like this, right, is equal to 0. So 20 minus 6I1 minus 14I2 is equal to 0 is our equation, or 6I1 plus 14I2 is 20. Solve these two equations and you can find out I1 and I2, right? So super mesh analysis is done in this form. Okay. So now let us consider another super mesh analysis. We'll just write the equations, and when we are seeing this, we can see that there are three meshes: mesh 1, mesh 2, and mesh 3, and the currents I1, I2, and I3 have been already given. If it is not given, you will assign random directions. Like I said, normally better to assume clockwise directions, right? So once it is done, meshes 1, we identify that mesh 1 and mesh 3 form a super mesh here. Why? Because this is mesh 1, this is mesh 3, and they have a 7 ampere in common. So when we are writing the equation, so write the super mesh equation first and write the KVL for this by removing the 7 ampere source. So when we are removing the 7 ampere source, it looks like this, right? So this is when I'm writing the KVL for this. How does it look like? We are going to be removing this, and this is mesh 1, this is mesh 3. So this is mesh 1. This was the 7 ampere source which I've removed. Then this is your mesh 3, and this is how you're coming back. So writing super mesh consisting of mesh 1 and mesh 3. By removing the 7 ampere source, we are going to be writing the equation for this. So what is the equation going to be? It is going to be 7 minus 1 into. Now, this 1 ohm resistance is common to mesh 1 and mesh 2. So which means it has a current of I1 minus I2. Since I am considering mesh 1 and mesh 3 here, mesh 1 and mesh 3 currents are considered to be predominant, right? So when 1 ohm is common to I1 and I2, so I write the equation of this as equal to minus 1 into I1 minus I2, and remain then minus of 3 into, there is a current of I2 like this through 3 ohm, and I3 in this direction. So I3 is flowing from left to right through the 3 ohm. So minus 3 into I3 minus of I2. Right? Again, we have considered I3 current to be predominant. Right? I2 was flowing like this, and I3 is flowing in the opposite direction. So this is the direction of I3. This is how the current is flowing. So I3 minus I2 is the current through 3 ohm. Now, the 1 ohm resistance has only I3, so it is minus 1 into I3 is equal to 0. So this is our super mesh. So KVL for super mesh. This is the KVL for super mesh. Now, what is the KCL equation for the super mesh? That is considering the 7 ampere. So 7 ampere current is common to the meshes 1 and 3, and 1 is flowing downwards, 3 is flowing upwards, I3 is flowing upwards, which means 7 ampere is flowing following the direction of I1. So I'll write it as 7 is equal to I1 minus of I3. So I1 is flowing down, I3 is flowing up, and these are our two equations. Coming back and solving this, so we had written two equations now. One was for the super mesh. So here there are three meshes. So we require, and three unknowns are there. So we require three equations. So one equation is the KCL equation. One was the super mesh, and the third one will be the equation for the mesh 2. So the third equation is going to be normal mesh analysis for mesh 2, which is going to be equal to, so minus 2I2. This 2 ohm has I2 flowing through this 3 ohm. This 3 ohm has I2 and I3 flowing through this. 3 ohm has I2 and I3. So following the direction of I2, I2 minus I3 minus 1 into I2 minus I1 is equal to 0. So in this case also, I2 is flowing upwards to 1 ohm, sorry, and I1 is flowing in the downward direction. So, which means that you have, and since you are writing the equation for mesh 2, you are going to be ending up with this equation. So, we have got three equations. Obviously, 3 unknowns, 3 equations. Solving this, we get the next step. So solving, you get I1, I2 and I3. And the current through the 3 ohm resistor was asked. So this was 3 ohm. So 3 ohm has a current of I2. So in this case, I2 is 2.5 ampere and I3 is 2 ampere, which means the current through the 3 ohm resistor is 0.5 ampere in the direction of I3, which is from left to right. Right. So this is how the problems are solved. So again, repeating that for super mesh, first what do? Is we write a KCL equation for the current source, which is common to two of the meshes, right? Then by removing the current source, you write the KVL equation for the super mesh. Remember, when I'm speaking about super mesh, it is mesh 1 and mesh 3 which we are considering here, right? So once that is considered, so 2 equations are already done. The third equation will be for the normal, which is not a part of the super mesh. I2, mesh 2 is not part of super mesh. So write normal KVL or normal mesh analysis for the mesh 2. Then you get 3 equations, you solve them. This is the steps which are followed. Okay. Now let's observe this mesh. So you can see that there are 2 current sources, 2 ampere and 4 ampere. Uh, but at the same time, is it a super mesh? So let's observe this. Now, what is the condition of a super mesh? That there is a current source which is common to 2 meshes. So if this 2 ampere or the 4 ampere, is it common to any mesh? No, right? So 2 ampere and 4 ampere both are on the outermost loop. So which means that it is not common. So 2 ampere is not common to any 2 meshes. Similarly, 4 ampere is also not common to any 2 meshes, which means that this is not a super mesh problem. Now, and if I designate the currents like this, that is, suppose if I call this as I1, this as I2, and this is I3, you can immediately see that I1 is nothing but the current. I1 is a mesh current through this mesh, and you can see that 2 ampere is also flowing through this. So at this immediately we can say I1 is 2 ampere. Similarly, if you observe this, I2 is a mesh current here, and we have the 4 ampere flowing through this. 4 ampere is in the opposite direction to I2. The value will be, so value of I1 is going to be equal to 2 ampere, and I2 is going to be equal to minus 4 ampere, right? So we know I1 and I2. So we only require to find I3. So I3 is the only unknown. So here you write, so you can write the mesh equation here for I3, for the mesh 3, and find out I3. So basically there's only one unknown in this case. So many times in some problems we have conditions like this where there will be a current source in the outermost loop. So it will not be a super mesh problem in that case. So the current sources which are there in the outermost branches are not considered a super mesh. This is what we want to clarify. Okay, mesh analysis can also be used in AC. So in AC circuits also mesh analysis can be used like the normal way. The mesh currents are assigned, and when there are number of voltage sources, we go for mesh analysis. We can write mesh equations by KVL for AC also. Okay. So here we have the problem of of an AC circuit where the input is 100 angle 45. There is a resistance 3 ohm in series with an inductive reactance. So J4 is an inductive reactance. You can see that the unit is ohm. There are 2 inductances here and there is 1 capacitance. Their reactances have been given. So ohm shows that the reactances have been given, not the value of the inductance or not the capacitance values, but the reactances have been given. Now, from our basic principles or basics of voltages across resistance and inductance, we know V is equal to I into R, right? In AC, so this is in the case of DC circuits where we have only resistances. Now, if you have an AC circuit, we can write V is equal to I into Z, where Z is equal to R plus or minus J into X, right? Now, this X can be either XL is called as the inductive reactance, right? XL is the inductive reactance, unit is ohm, and XC is the capacitive reactance, that is also unit is ohm, right? So now if you're representing, inductive reactance XL is normally written as, it is actually J into XL. So J into L omega. That is how you represent. So L omega is your reactance, right? Similarly, XC is minus J by C omega. This is how the values are. So here we have been given the value of L omega. So here in this case, if you see J4, J4 is the 4 is the value of, is nothing but L omega. Similarly, here it is a minus J10. So 10 is nothing but 1 by C omega. So the minus J indicates that's the capacitive reactance, plus J indicates it's an inductive reactance, right? Now, once we know this, what we are going to be doing is just writing the equations, writing the KVL equations like in normal case, normal mesh analysis, writing the KVL for this. So if I go around the first loop, I have 100 angle 45 minus of the total. Now we have the resistance and inductance are both in series. So the total reactance is 3 plus J4. So I'm going to be combining these two and writing it as 3 plus J4 into I1 minus of J10. Now J10 is common to both meshes 1 and 2. So it has an equivalent current of I1 minus I2. Like, so the remaining part remains the same only. So only thing what is different is that we are writing in terms of the inductive and capacitive reactance. So that is for the first loop, and for the second loop it is going to be so I'll start like this, start from the from this and go here like this. So it is minus J10 and the current is I2. So your you can see that as the current flows like this, it is going to have a polarity like this. So plus to minus is a negative. So minus of minus J10, that is a value I2. That is what, right? So the polarity, the voltage drop is negative. So that is what we have. The voltage drop like this from positive to negative is a negative. Sorry, positive to negative is a negative drop in polarity, which is denoted by the negative. The value of the reactance is minus J10, right? So this reactance into the current, which is I2. So this is what we have written over here, and minus J10 into minus I2 minus of J10. This is for I2 minus I1 is equal to 0. So this minus J10 is for this component, that is the inductive component which we have, right? So we are going like this, and minus J10 into I2 minus I1 is equal to 0. So mesh analysis is written in the normal way. So this can be solved, and once you solve this, you get the equation as I2 is 10 angle 45. So if you solve this, you get I2 is equal to 10 angle 45, and also I1 is equal to 0. So I1 comes out to be 0. So this is after solving. Only thing is AC solving takes a little more time than when we are solving DC circuits. So you can write the equations like this properly. That is how it is done. Okay, so summary. We have discussed mesh analysis and super mesh analysis in this video. So mesh analysis and super mesh analysis both apply KVL. In super mesh, there is a current source which is in common to two meshes, and at the same time super mesh analysis involves a KVL and a KCL equation. So the KCL, as we saw, the KCL equation is used for the current source. So when you're writing the KCL equation, the current source which is common is expressed in terms of the KCL equation, and the KVL is for the two meshes without the current source. Without current source. So with the current source excluded, you write KVL for both the meshes together in one equation, right? So this is in one equation. So we have got a KVL for the supermesh. There you have got a KCL for the supermesh. The KCL is for the current source, right? So the current source is written in terms of the mesh currents. That is also another thing. Current source is written in terms of the mesh currents. Mesh currents, right? So once we write this, you ignore that. So this equation, so one equation you have written using KCL. Now you ignore the current source and write KVL for the both the meshes, but without the current source. So this is how we are doing supermesh. Also, we have discussed supermesh for AC circuits also. So AC circuits are a little more tedious to solve, but the same method will be used for so both supermesh or mesh analysis. Okay, so that is about mesh analysis. Thank you.